Good morning. I warmly welcome you to the International Open University Research Sessions IOURS 2022.
IOURS 2022 is an important annual event of the Open University of Sri Lanka. IOURS established itself as a high-caliber research forum that attracts not only researchers from the OUSL community but also other state universities and higher education institutes as well as overseas researchers, creating a forum for presenting and discussing valuable research findings leading to enriching experience to the researchers. IOURS significantly contributed to enhance the research culture among the OUSL staff members in ODL, open and distance learning, and disciplinary-based research areas, which directly inspired our staff members to participate at other international and national and international conferences by contributing quality research findings. That IOURS 2022 will bring you renewed motivation and enthusiasm to engage in more productive research.
IOURS 2022 provides an opportunity for sharing knowledge created through research across various disciplines. I am particularly pleased with the choice of this year's theme, that is, Contemplations Towards Next Normal for a Smart Future, Directions and Dimensions. This is an approach emphasizes the requirement for educators and researchers to embark on creative thinking to formulate strategies to overcome unforeseen contingencies. Therefore, no doubt that this conference aims at breaking away from the traditional models of higher education and opening doors to new, innovative, creative and visionary conceptions. And this will also be a stepping stone for further development of Open University of Sri Lanka's national and international advocacy campaigns.
I'm delighted to introduce our chief guest, Professor Dr. Ebba Ossianilsson. Professor Dr. Ebba Ossianilsson from Sweden is an independent consultant, expert, influencer, and quality auditor in the field of open, flexible, online, and distance learning.
Thank you so much for the kind invitation to participate at your and contribute to your wonderful conference. It's a great pleasure and honor for me to be chief guest at your prominent conference with a timely theme on the contemplation towards the next normal for a smart future, directions and dimensions.
The research sessions of the Open University of Sri Lanka is a very important annual event of the OUSL calendar that is indeed much looked forward by all tiers of the university. However, there is certainly a lot of groundwork that was involved in organizing the conference from inception to reality. Ladies and gentlemen, on behalf of the organizing committee, I'm honored to be here this morning to thank all those whose contributions have made today a reality.
The first keynote speech of IOURS 2022, which will be delivered by Professor Arjuna Parakram.
I see my role today as trying to do precisely that. I want to talk to you about the serious issues that we face. I want to encourage you to contradict me, to argue with me, to fight with me, so that we can produce a kind of engagement that goes beyond the platitudes of our times. So I hope, I'm very privileged to be here, and I hope that you will not decide that you made the wrong choice after you hear me talk. My title is Resisting the Aftershock Dogma, Rejecting Neoliberal Economic Policy as the Engine of Change in Educational Principles and Practice.
Good morning. Paper ID number 6, we have already joined.
Very good morning to everyone. Welcome to IOURS 2022. And this is the day 2 of the IOURS 2022 on international conference. And we will now commence the online session 4, right? And parallel on online session 3 under the theme Physical Sciences. Let me introduce our session chair. He will chair the parallel session on online session 3. Our session chair will be Professor R. Senthilnidhi, Professor in Chemistry. He is the current head of the Department of Chemistry, Faculty of Natural Sciences, the Open University of Sri Lanka. I cordially invite Professor Senthilnidhi to chair the session. Over to you, sir.
Thank you, Dr. Vasana. Good morning to you all. I would like to welcome you all to this virtual conference, IOURS 2022. There are 5 presenters in this session. Every presenter will have 15 minutes for their presentations. After that, we can have 5 minutes for the Q&A session. Any others, I request, and others, I request the outset to mute your microphones. Then the time comes again, you unmute the microphones and ask your questions. Now I invite the first presenter, W.I. Sandamali. The presentation is enhancing the photocurrent by titanium oxide nanofibers in lead sulfide quantum dot sensitized solar cells. So time to Sandamali is over to you.
I'm Shara Sandamali from the Open University of Sri Lanka. This study is enhancing the photocurrent by TiO2 nanofibers in lead sulfide quantum dot sensitized solar cells. And it is based on the research work carried out in the National Institute of Fundamental Studies, CANDI. Content of this presentation is introduction, methodology, research and discussion, conclusion and references. As a brief introduction to quantum dot sensitized solar cells, QDSSCs. QDSSCs are a type of third generation solar cells where quantum dots are utilized as the light captivating material. Quantum dots are semiconductor nanocrystals exhibiting quantum mechanical effects which comes to effect when their size approaches the size of the excitant Bohr radius. They can absorb light photons and generate electron-hole pairs, initiating a flow in current. Some examples for quantum dots used for this purpose are cadmium sulfide, cadmium telluride, and lead sulfide. This study is based on lead sulfide PBS QDSSCs. Main components of the assembled solar cell are shown here. QDSSCs mainly consist of a photoanode, electrolyte, and a counter electrode as shown in this schematic diagram. Photoanode is fabricated through the deposition of mesoporous semiconductor material on a conducting glass substrate. And then it is sensitized with quantum dots. Electrolyte contains a redox couple which is filled between the photoanode and the counter electrode. Counter electrode is used for the charge exchange. Upon illumination, quantum dot is excited to a higher energy state and excitons are created. Due to the band alignment, excited electrons are injected to the conduction band of the TiO2 and the holes are scavenged by the electrolyte. Electrons diffuse through the mesoporous TiO2 and reach the conducting glass substrate and then enter the external load to perform work. Then these electrons reach the counter electrode and regenerate the oxidized component of the redox couple in the electrolyte. And in this study, TiO2 photoanode based PBS QDSSCs have been fabricated with polysulfide electrolyte and a copper sulfide counter electrode. In order to enhance the performance of the solar cells by enhanced light absorption by light scattering, photoanodes were modified with TiO2 nanofiber layer. Methodology. This is the procedure followed in preparation of the photoanodes. First, a pinhole-free compact layer of TiO2 was deposited on a pre-clean FTO glass substrate by spin coating a mixture of titanium isopropoxide, propanol, glacial acetic acid and nitric acid in an ethanol medium at 3000 rpm for 1 minute. The substrate was sintered at 450 degrees Celsius for 45 minutes. The above substrate with the compact layer was then covered with the paste prepared by TiO2 P90. For that, 0.25 gram of TiO2 P90 powder was ground well with 1 milliliter of 0.1 m nitric acid. The paste was spin coated on the TiO2 compact layer at 3000 rpm for 1 minute and similarly sintered at 450 degrees Celsius for 45 minutes. This is the modified layer of the photoanode. On top of the TiO2 P90 layer, a TiO2 nanofiber layer was deposited. For that, a viscous solution of titanium isopropoxide was prepared by mixing with polyvinyl acetate, dimethylformamide and glacial acetic acid by magnetic stirring. A TiO2 nanofiber layer was deposited for 20 minutes with a solution flow rate of 2 ml per hour on the TiO2 P90 layer by the electrospinning technique as illustrated here. Next, the electrodes were sintered at 450 degrees Celsius for 45 minutes. Then, the prepared TiO2 electrodes were sensitized with PBS quantum dots using successive ionic layer adsorption and reaction (SILA) technique. TiO2 photoanode was first dipped in an aqueous lead nitrate solution, followed by washing with distilled water, drying and dipping in an aqueous sodium sulfide solution, followed by again washing with distilled water. After a few cycles of this procedure, photoanodes were dried and heated at 100 degrees Celsius. Finally, the photovoltaic device was completed by clipping the prepared photoanode together with the copper sulfide counter electrode prepared by depositing copper sulfide on a brass plate and injecting polysulfide electrolyte in between them. And for a comparative study, another set of photoanodes were prepared by Dr. Bladin TiO2 P25 paste on TiO2 P90 instead of the TiO2 nanofiber layer. results and discussion. These scanning electron microscopy images show the top view of the TiO2 nanoparticle in figure A and top view of the nanofiber layer in figure B, and the size of the nanofibers with the average diameter appears to be between 30 to 80 nanometers according to figure B. This nanostructured layer enhances the light absorption of the photoanode by multiple light scattering. Absorption studies of the photoanodes. This figure shows the absorption spectra of the PBS quantum dot incorporated TiO2 nanoparticle and nanofiber electrodes. The nanofiber photoanode shows increased absorption, which is due to the increased scattering in the electrode, and more light can be absorbed due to this. This figure shows the current voltage characteristics of PBS QDSSCs fabricated with TiO2 nanoparticle layer photoanode and TiO2 nanofiber photoanode under the light illumination. TiO2 nanofiber photoanode shows better photovoltaic performance than TiO2 nanoparticle photoanode as shown here. QDSSC with TiO2 nanofiber shows about 11.64 milliampere per square centimeter current density, while QDSSC with nanoparticle shows only 9.22 milliampere per square centimeter current density. Fill factor of the TiO2 nanofiber device has also increased, while overall power conversion of the nanofiber device has increased to 3.92% compared to 2.95% of TiO2 nanoparticle device. Both current density and efficiency show significant enhancement here. This is due to more light captured by quantum dots, as the scattering light extends the traveling distance of incident light. Conclusion. QDSSC with TiO2 nanofiber photoanode shows an efficiency of 3.92% with a higher short circuit current density. The enhancement in overall power conversion efficiency of the PBS QDSSC with nanofiber photoanode relative to the nanoparticle photoanode is about 33%, and the current density enhancement is about 26%. It can be concluded that the enhancement in short circuit current density is evidently due to the increased light absorption by multiple light scattering. And we acknowledge the support given by ahead operation of the Ministry of Higher Education funded by the World Bank for this study. These are some of the literature referred during this study. Thank you for your kind attention. I'm Ishara Sandamali from the Open University of Sri Lanka. The title
Yes, mic and video can. Video can. Thank you, Sandamali. It's a very interesting presentation. Now the presentation is forum is open for the discussion. In the absence of Sandamali, Jasidharan will answer for your questions. Jasidharan?
Yes, good morning, everyone. I am here.
Good morning. Yeah. Okay. Any questions from the audience? Any questions from the audience? Yes, Jasidharan, it's not a question. Since I am a chemist, I want to know some chemistry behind this work. That's why I'm asking certain things to you. why you are interested in the lead sulfide, PBS? Is there any specific reason you select PBS quantum dot? Yasidaran? Yasidaran? Yasidaran, your voice is not coming here. Yasidaran, your voice is not coming.
Usually,
Not clear, Yasidaran.
solar cells. Can you hear me? Can you hear me? Now it's okay, I think.
Something, okay, yeah, okay. You continue.
Yes, in the case of lead sulfide, for example, in the dye-sensitized solar cell, one dye molecule will give the one electron hole pairs for absorbing one photon, but this has ability to multiple exciton generation in the quantum dots in the lead sulfide. And it has a wide range of absorption from visible to near IR. Then we can harvest the most of the sunlight for this purpose.
Did you try with some other metal, for example, lead and the Sanasa in the same group in periodic table?
Yes, we already did for SNS, you mean tin sulfide.
Also. Yeah,
the
efficiency is
very low, very low because by comparing with PBS.
Lead sulfide. That's the reason you. Okay.
Yes.
And you say that one in this solar cells were fabricated using PBS quantum dot sensitized titanium oxide. Yeah, the fabrication. How do you done the fabrication? Did you use any solvents?
Just as we just did for the Sela cycle, that is a chemically we synthesized in the Sela cycle. We had the two precursor solution, PB2 plus solution and S2 minus solution, 1.1 molar.
Yeah.
Then successive ionic layer absorption and reaction method we synthesized, a very simple method, but that method we can control the size of the quantum dots.
But you are not using any organic solvents for the fabrication?
No. We used only aqueous solution for lead nitrate and sodium sulfide.
Just aqueous solution just for a PB form PBS. That is you are using that one. Then you believe that nanoparticles form the fabrication is completely work that one?
Yeah, it's work because I confirm with here we didn't. I think here we didn't. Report that PBS TEM image of the PBS quantum dots, but that image we have that image.
You are satisfied. You are satisfied.
Yeah. Because I already control the size of the quantum dots, and I got the TEM image with number of Sela cycles increase and increase. Size of the quantum dots will increase. But big size may be reduce the efficiency. Some 10 to 20, that size of nano quantum dots are performing well.
But then I think it is better you in future you use some organic solvents, polar solvents, and highly polar solvents you use, then the quantum dot, the lead sulfide quantum dots will be very good one for you.
Yes, because this time also now we didn't do this, but later we did to change the surface charge of the TiO2 becomes a negative charge. Then PB2 plus may easily attach first. Then efficiency is increased now. Later we prepare.
Okay. Any other questions? Any other questions? Okay, since no more questions, we thank to the Sandamali and Jasidaran, GKR Senadira, BPS Pereira, JCN Rajendra, and in Karthikeyan, LA Vijayanayaka, MKAL Disanayaka. All of the others, and also again, and we conclude this presentation, right? The next presenter is again Sandamali. The topic is effect of gold plasmonic nanoparticles on the short current circuit density for the lead sulfide quantum dot sensitized solar cells. So time to you, Sandamali.
I'm Ishara Sandamali from the Open University of Sri Lanka. The title of the study is Effect of Gold Plasmonic Nanoparticles on Short Circuit Current Density of Lead Sulfide Quantum Dot Sensitized Solar Cells. And this study is based on the research work carried out with the National Institute of Fundamental Studies, CANDI. This is the outline of the presentation: introduction, methodology, resource and discussion, conclusion and references. Introduction. Manifestation of a resonance effect due to the collective oscillation of valence electrons of metal nanoparticles stimulated by incident photons is known as localized surface plasmon resonance or LSPR effect. When electric fields of light are directed at nanoparticles, the surface plasmons become excited and begin to resonate. This electric field creates a separation of charge, which then forms a dipole oscillation in the same direction as the electric field of light. As the frequencies are the same, the SPR allows a strong absorption of the incident light, while also allowing some scattering of light. This study focuses on how to utilize this LSPR effect of gold nanoparticles in efficiency enhancement of quantum dot sensitized solar cells, QDSSCs. QDSSCs are a popular study area in third generation of solar cells due to their low production cost and the excellent properties of quantum dots, such as ability of multiple exciton generation, durable energy gap due to the quantum confinement effect, and high molar extinction coefficients. QDSSCs have three basic components: photoanode, counterelectrode, and electrolyte, as shown in this schematic diagram. In this study, TiO2 photoanode-based lead sulfide QDSSCs have been fabricated with polysulfide electrolyte and a copper sulfide counterelectrode. PBS quantum dots generate electron-hole pairs by light absorption. These electrons get injected to the conduction band of TiO2 and flow to the external circuit, finally reaching the copper sulfide counterelectrode. Polysulfide redox couple regenerate PBS quantum dots and transport holes to the counterelectrode. In this study, colloidal gold plasmonic nanoparticles were added to the TiO2 photoanode in order to enhance the performance of QDSSCs by using their LSPR effect. Methodology. In order to prepare gold nanoparticle colloidal solution, first a 0.1 m trisodium citrate aqueous solution was prepared. 2 ml of the solution was added to 20 ml of 1 millimolar tetrachloroauric acid boiling under continuous stirring. When the color of the mixture becomes deep red, the heat was turned off and the solution was allowed to cool. When preparing photoanodes, a compact layer of TiO2 was first deposited on a pre-cleaned FTO glass substrate by spin coating a paste prepared with TiO2 P90. For that, 0.25 gram of TiO2 P90 powder was ground well with 1 milliliter of 0.1 m nitric acid. The paste was spin coated on the FTO glass at 3000 rpm for 1 minute and sintered at 450 degrees Celsius for 45 minutes. Then, a paste of TiO2 P25 was prepared by mixing with 1 milliliter of dilute nitric acid, a drop of polyethylene glycol and a drop of Triton X100 and 0.25 gram of TiO2 P25. Different amounts of gold nanoparticle colloidal was added and the paste was ground again. The TiO2P25 nanoparticle paste containing gold nanoparticles was spin coated on TiO2P90 layer at 1000 rpm for 1 minute. Finally, the electrodes were sintered for 45 minutes at 450 degrees Celsius. In order to assemble complete photovoltaic device, fabricated photoanodes with effective area of 0.12 square centimeters were sandwiched with copper sulfide counter electrodes using steel clips, and an appropriate amount of polysulfide electrolyte containing sulfide polysulfide redox copper was injected in between. Following characterization methods were used during the study: optical absorption spectra by UV visible spectrophotometer, TEM imaging by high-resolution transmission electron microscope, and current voltage characterization under simulated light. Research and discussion. The first figure shows the high-resolution transmission electron microscopy images of the gold colloidal nanoparticles. According to the HRTEM image, it can be seen that the sizes of the gold nanoparticles are in the range between 25 and 35 nanometers. The EDX spectrum of the TiO2 gold PBS photoanode shown here confirms the existence of gold, lead, and sulfur in the TiO2 electrode. Figure A shows the optical absorption spectrum of plasmonic gold nanoparticles. It shows a broad absorption in the visible region, which peaks around 527 nanometers. From this absorption maximum, the average particle size of the gold nanoparticles has been approximately estimated by comparing with the published articles, which is in the range of 25 to 35 nanometers. This result was confirmed with TEM images. And the figure B shows the optical absorption spectra of TiO2, TiO2 gold, and TiO2 gold PBS electrodes. Gold nanoparticle incorporated electrode shows a broad peak in the visible region between 500 nanometers and 550 nanometers. This peak clearly confirms the presence of gold plasmonic nanoparticles in the TiO2 electrode. TiO2 gold PBS photoanode shows a similar broad peak around 500 to 550 nanometers. Also, this photoanode exhibits another very strong absorption peak around 1050 nanometers in the near IR region, evidently due to the optical absorption by PBS quantum dots. This figure shows the current voltage characterization of TiO2 PBS photoanodes with and without gold nanoparticles under the simulated light conditions. Gold nanoparticle incorporated PBS quantum dot sensitized solar cells show improved photovoltaic performance compared to the control device. This is evidently due to the enhanced photocurrent in the QDSSC with gold nanoparticles compared to device without gold nanoparticles under similar fabrication and light conditions caused by the LSPR effect of gold nanoparticles. According to the photovoltaic parameters summarized in Table 1, QDSSC with gold nanoparticles show 13.12 mA per square centimeter current density, while QDSSC without gold nanoparticles shows only 9.71 mA per square centimeter current density, while the overall power conversion of the device has increased to 4.24% from the 3.09% of QDSSC without gold nanoparticles. QDSSC with gold nanoparticle photoanode shows an efficiency of 4.24% with a higher short circuit current density. The enhancement in overall power conversion efficiency of the PBS QDSSC with gold nanoparticles relative to the device without gold nanoparticles is about 37%, and the current density enhancement is about 35%. This is evidently due to the enhanced photocurrent in the QDSSC with gold nanoparticles caused by the localized surface plasmon resonance effect. This research was supported by the head operation of the Ministry of Higher Education, funded by the World Bank. These are some of the literature referred during the study. And thank you.
Thank you, Sandamali. Now the forum is open for discussion. Again, in the absence of Sandamali, Jasidharan will answer for the Q&A sessions. Is there any questions? Is there any questions, please? Yes, in the absence of questions, we will thank to the same group of team that Jasidharan, Sandamali, GKR Senadira, BPS Pereira, JCN Rajendra, N. Karthikeyan, LA Vijayanayaka, and MAKL Disanayaka for their interesting presentation. Right. Next, we move to the next presenter. A mathematical model for hard time windows vehicle routing problem with moving shipments at the cross-dock centers. SR Jnanapragasham, WB Danundasegar. The presenter will SR Jnanapragasham. Jnanapragasham, it's a time for you.
We have formulated a mathematical model for the hard time windows vehicle routing problem with moving shipments at the cross-dock center. Initially, products were transported from a set of suppliers to a set of customers directly. It caused more cost due to their capacities, which are less than their truckload. Then, traditional warehousing centers were introduced in supply chain to utilize full truckload. Receiving, storing, sorting, packing, picking and shipping are the operations taken place at those warehousing centers. More than 30% of the total cost of product is due to the operations at those warehousing centers. Later, cross-docking strategy was initiated in 1930s by Walmart, but it became popular in 1980s. This strategy eliminates more costly operations at traditional distribution centers such as storing, tagging and picking. Up to 70% of warehousing cost can be reduced by implementing cross-docking strategy in supply chain. The most suitable products for cross-docking are perishable products that require immediate shipment, high quality products that do not require quality inspections, pre-tagged products that are ready for sale, promotional products during seasons, products with a constant demand. Among three levels of decisions at cross-dock center, strategic, tactical and operational, we concentrate only on operational level, which has several problems to be studied, such as scheduling, sequencing and assignment problem. But we mainly focus on vehicle routing between components of supply chain. In a general vehicle routing problem, the depot functions only as distribution center. But in vehicle routing problem with cross-dock, the cross-dock center functions as transshipment center, as at first phase it receives products from suppliers and at the second phase it sends products to the customers. Research on VRPCD was initiated in 2006 and then time windows characteristic was added to VRPCD in 2009, and there onwards it gets more attention among researchers as well as practitioners. Several research on vehicle routing problem with cross-docking and time windows had been conducted in the past by considering many characteristics. But in this study, moving shipment at cross-dock center is considered as a new aspect. Characteristics added to vehicle routing problem with cross-docking through this study are moving shipments. It is an operational internal operation. Two different sets of vehicles with two different capacities. Loading and unloading shipments in terms of both time and cost at all the nodes, including doors of cross-dock center. And finally, the hard time windows. Therefore, the objective of this study is to minimize the total cost, which contains 5 components. Number 1, transportation cost between nodes. Number 2, service cost at the nodes. Number 3, service cost at doors of cross-dock center. Number 4, vehicle operation cost. And number 5, moving shipments cost inside the cross-dock center, while satisfying added characteristics in time window, vehicle routing problem with cross-dock and moving shipments model. At the pickup process in our model, the collected products by inbound vehicles from suppliers are unloaded at cross-dock center. Then, at the consolidation process, the unloaded products at the indoors are consolidated and moved to outdoors to load them into outbound vehicles. Finally, the loaded products are delivered to relevant customers at the delivery process. It is emphasized that all the nodes have their preferred service time as time windows. The time components considered in this model are service time at each node and doors at cross-dock terminal, arrival time to each node, departure time from each node, moving time from indoors to outdoors at cross-dock center, and finally the ready time at outdoors at cross-dock center. A mixed integer nonlinear programming model is developed. The model is coded in Lingo optimization software. Branch and bound algorithm is used to solve the model. To test the developed model, we randomly generated some instances based on the following parameters, which are in the standard form. Solution of a particular instance with 4 suppliers and 6 customers are drawn in this figure. The sequence of nodes in each route is also indicated with directions in this figure. It clearly shows that 3 inbound vehicles are needed to collect from 4 suppliers in the left hand side of the center. At the same time, 4 outbound vehicles are needed to deliver to 6 customers in the right hand side of cross-dock center. This table presents the route-wise results of the instance reported in the previous slide. In each route, the quantity, lower and upper bounds of time windows, arrival time, service time of every node are included. It is highlighted that the ready time at the outdoors to start the delivery process is 382 minutes, and the completion time of the entire process is 750 minutes. Here we have summarized the results of 16 instances. For example, in the 6th instance, which I pointed out in the previous 2 slides, to collect 150 units of products from 4 suppliers, 3 inbound vehicles are needed, whereas to deliver them to 6 customers, 4 outbound vehicles are needed. The total cost, the optimal solution, to perform the process is 3,887 cost units. These results can be obtained by our model on average in 0.75 seconds. The average computational time is determined in a way that the same instance was executed 10 times. Similarly, the results of the rest of the instances are also summarized in this table. The conversion rate of the model is also analyzed here. We plot the curve of average computational time versus problem size. Accordingly, the curve is fitted to exponential. The coefficient of determination value as goodness of fitted curve is 98%. The findings from this study are as follows. Since the computational time is reasonably less, the proposed model can be used for last time planning to schedule the routes. The convergence rate of the problems considered in this study is exponential. That means when the number of nodes increases, consequently the computational time to reach the optimal solution increases exponentially. It is recommended for further studies that heuristic or meta-heuristic methods are more appropriate to solve the medium and large-scale problems. Revise the proposed model according to the following constraints: availability of vehicles for transportation, capacity of temporary storage at cross-dock center, budget allocation for transportation. So these are the references cited in this presentation, but we have referred more than this. Thank you.
Thank you, Jnana Prakasam. Now the presentation is open for discussion. Any questions? Presentation is open for discussion. Any questions? Jnana Prakasam, it's not a question. What I am asking is, you are using the Lingo optimization software.
Yes.
It is an open source fund.
Yeah, Lingo is open source.
It's open
but
source
we
fund.
use the commercial version. We used the commercial version. There are some trial versions also, but the constraints are limited for that. The number of variables are limited. So we used the commercial version.
Are your university purchased that one?
Yeah, from the university they
purchase. Okay. Then the number of nodes, you are saying that in your trials, how many number of maximum, how many number of nodes you are trying? About 50 or 100?
No, we used only for the small cases. There we used up to 16 in both sides. Number of suppliers and number of customers, both sides 16. Though that's the standard.
16. 16.
Yes, Lingo is not
for
capable
that,
of
the time. What's the time computational time for 16?
I think if the host displayed number 70, the slides number 70 is there. For each and every problem, the number 6.
Slide number 17. 17 slide.
Yeah, here the last column represents the computational time.
Computational
for
time
each and every instance.
In seconds, huh?
Yeah, in seconds.
Okay, good. Any more questions? Since no more questions, we thank to Sr. Jnana Prakasam and the other co-author WB Danusasagara, and we conclude this presentation and we move to the next presentation. Electrochemical removal of salt ions via capacitive deionization using electrodes, fabrication from locally activated carbon. The authors are H.O. Veerakodi, D.S. Alvis, N.D. Silva, Y.Y. Kannangara. The presenter is H.O. Veerakodi. Veerakodi, it's a time for you.
I'm Oshini Veerakkodi and I'm going to present our presentation. The topic is electrochemical removal of salt ions via capacitive deionization using electrodes fabricated from locally activated carbon. First of all, we come to the introduction of the CDI. Capacitive deionization emerged as a low-cost, energy-efficient and environment-friendly technology for desalination. This process of electrosorption occurs at two electrodes for removing ions from feed solution. You can see in this picture, when we apply an potential to the electrodes, they are charged positively and negatively. The cations and anions move to the polarized electrodes and create electrical double layer and removing ions from the feed solution. The adsorption capacity and electric conductivity of the electrode highly depends on the electrode material. For high performance of the CDI, the carbon is the choice as porous electrode material. The specific surface area, pore size, distribution improve the high salt electrosorption capacity. Furthermore, the used material should be stable and no chemical degradation for electrode occur in voltage window applied for CDI. Lastly, the cost of the electrode material are important to take into consideration. Nowadays, activated carbon is the commonly used material because of most cost effective and it has high specific surface area. Under the experimental method, we are going to discuss the surface modification of activated carbon and fabrication of electrode. First, we talk about the surface modification of activated carbon. The carbon sample was impregnated in 2:1 ratio in nitric acid for overnight, then washed with distilled water until pH was neutral. Dried in the oven at 120 Celsius for 4 hours. After that, carbon sample was grounded and ball milled for 12 hours. The fabrication of the electrode with surface modified activated carbon. Acid treated surface modified activated carbon was mixed with conductive additive and polybond binder in 8:1:1 ratio. Slurry was cast on the current collector using the thin film applicator. You can see in this picture the thin film applicator, and kept the electrode in room temperature 24 hours for curing. After that, the heat treated at 150 Celsius. Then we move to the characterization method. We can see the resistance of current collectors. We selected 4 types of current collectors: graphite sheet, stainless steel plate, aluminium sheet and aluminium foil. The stainless steel plate was selected as the current collector because of low resistance. Then come to the characterization of activated carbon. When we compare the BET results of the activated carbon, the surface area of non-treated activated carbon is 1289 meters square per gram, and the surface area of the treated activated carbon is 1562 meters square per gram. And you can see SEM images of activated carbon before treated and after treated. Here we measure the electrochemical performance. We measure the specific surface area according to the equation, and the optimum value for the specific capacitance is 73.15 farad per gram when the scan rate is 10 milliwatt per second. This picture describes the CDI setup. The setup was carried out in a flow-through mode with the cycle pass. Conductivity measurements using 193 microsiemens per centimeter for sodium chloride corresponding to 100 ppm. The optimal ion removal capacity was 9.6 milligram per gram. Here we measured that value from ion adsorption capacity equation. These are the references. Thank you.
Thank you, Virakodi. Now the forum is open for discussion. Any questions? Any questions? Yeah, Virakodi, it is not a question, but I want to know whether it is the concept is okay. The desalinization of the water using a cultivated carbon is concept is okay, it's work. But for the application, what you are present in your abstract, you say that one to overcome the problem of the seawater desalinization, whether it is for that scale, it is possible to do this one. This how much it costs for this plant and all these things. It is a cost-effective one.
We usually,
for the
we
laboratory
usually
scale is
consider.
okay. Yeah, you tell.
Can you hear me?
Yes, tell.
Yeah, we usually consider 5,000 ppm to 100 ppm, the salinity level. Under the 100 ppm, we consider as the fresh water. More than 5,000 ppm is the moderate salt salinity level. In this project, we consider 1,000 ppm to 100 ppm concentration. The problem is when the concentration is increased, our current collector will be corrode, so that we concentration for this project.
That's why I'm asking whether for the seawater, the salination is, I think, not 5,000 ppm. I mean, it is very high, you
Yeah, moderate, more than 5,000 ppm is the moderate salinity level.
Yeah. Okay, is there any questions? Since no more questions, we thank to Virakodi, Ninula Alvis, Noan D. Silva, and Kannankara. And thanks again, and we move to the next presentation. Is fabrication of humidity sensor using carbonized nitrile butadiene rubber, NBR waste. The presenter is MD Madhuvansa. The co-author is GDK Keshan, RMG Rajabaksha, YY Kannangara, WPSL Vijay Singh. Madhuvanda, is a time for you.
Hello everyone, I am Dhanushka Madhuvanta and my research topic is fabrication of humidity sensor using carbonized nitrile butadiene rubber waste. My colleagues and supervisors are GDK Heshan, Professor RMG Rajapaksha, Dr. Yasun Kannangara and Dr. Sanjeev Vijayasinghe. As the introduction, before we discuss about the humidity sensors, first we should know what is meant by a sensor. A sensor is a device that can respond to the external stimuli such as temperature, gas, humidity, pressure, and convert them into a human-readable digital signal. Based on these external stimuli, a wide range of sensors have manufactured. Among them, the humidity sensors are the most widely used type of sensor in many fields such as food processing, industrial processes, health sector, agriculture, aerospace, chemical industries, pharmaceutical industries. Likewise, When we are fabricating a humidity sensor, we should consider some key factors like cost of the product, reliability of the process, simplicity of the process, likewise. That is why we choose NBR glove waste to synthesize the sensing material. As we know, during the last 2 years with corona pandemic, the usage of NBR gloves has increased remarkably. These gloves are used in many industries over the latex gloves due to the absence of allergic reactions. But the main problem related with the disposing of these gloves is the lack of proper disposal method. The two common disposal methods are the landfilling and the incineration. Both of these methods have a negative impact on the environment. That is why we propose a simple thermal treatment to convert these nitrile gloves into valuable added product. This is the proposed method of our to convert these nitrile gloves into a value-added product. First, we collected the nitrile glove samples from the laboratories and washed them with hot water and hexane to remove all the adhered impurities. Then the samples were sun-dried for 1 day. After that, the samples were cut into small pieces and mixed with the synthesized hydroxide into 1:1 ratio and carbonized in a tube furnace at 700 degrees in an inert atmosphere. After the carbonization, the obtained sample was grinded and converted into powder form to synthesize the sensing materials. The material was further characterized by using TGA, Raman, XRD, FTIR and the SEM technique. In the characterization, we carried out a thermal TGA analysis to study the thermal stability of the samples. In the TGA curve of pure NBR glove sample, we can see a slow degradation step up to 252 degrees due to the evaporation of plasticizers, additives and low temperature volatile components which are frequently added to the formulation of NBR gloves. After that step, two significant weight losses can be observed due to the heavy carbonaceous degradation of heavy carbonaceous organic compounds of the NBR rubber gloves, which are result from the chain scission of NBR at 780 degrees. 92.8% weight loss can be observed and 7.2% remain as the carbon residues. In the case of zinc hydroxide, significant weight loss can be observed around 85 degrees and followed up to 400 degrees. In the Raman analysis, so when the Raman and the XRD analysis, there are two significant peaks related to the D and G peaks can be seen in the both Raman spectrum of carbonized sample with and without zinc hydroxide. Additionally, a characteristic peak related to the E2 high vibration mode of zinc oxide hexagonal phase can be observed in the carbonized sample with zinc hydroxide around 436. The ID and the IG value has increased with the addition of zinc hydroxide in the sample, which due to the formation of more defects in the composite sample. In the XRD spectrum, we can clearly see both characteristic peaks related to the graphitic carbon and the hexagonal word-side structure of zinc oxide can be seen in the carbonized composite sample. In the FTIR analysis, we can clearly see all the characteristic peaks related to the raw NBR sample have disappeared after the carbonization of the sample with zinc hydroxide. Two dominant peaks related to the interatomic vibrational mode of zinc oxide can be observed in the fingerprint region of the carbonized sample. This further confirms the successful conversion of zinc hydroxide into zinc oxide. In the SEM images, in the first SEM image, we cannot see zinc oxide deposited on the carbon surface, but in the second image, we can clearly see the zinc oxide particles are deposited on the carbon surface. This structure is responsible for the fast decomposition of water molecules on the surface and increase the conduction mechanism. The fabricated sensor has good humidity sensing performances. In the first graph, the sensor showed a good linear relationship between the resistance and the relative humidity. Then the absorption and the desorption processes were repeated for several cycles, and it indicated the excellent repeatability of the sensor. The third graph, the fabricated sensor showed a good response time and the recovery time, which were 30 seconds and the 12 seconds. The stability of the sensor was tested for several hours at different humidity levels. The resistance was almost unchanged through the testing period, proving excellent stability and the durability of the sensor. These results show a good compatible of the fabricated sensor for high performance practical applications. My presentation is over. Thank you for listening. These are my references I use for prepare my presentation.
Thank you, Madhusanga. The forum is now open for discussion. Any questions? Any questions? Madhusanga, you are saying that one for the NBR polymer base, for the heat treatment, you are using 700-degree furnace temperature.
Yes.
Whether this furnace temperature you achieve in one stretch, or you are get this 700 step by step?
I achieve this temperature by 2 steps.
2 steps, but we are not mentioned that one, right? We are going straightly from 700 is
no.
This heat treatment is not fabrication is not possible, right? Something is some other it will happen, right? Other thing is, what is the advantage or the reason you select the NBR, nitrile butadiene rubber, rather than you go for a normal rubber based? Now the normal rubber based is very freely available in Sri Lanka. Then what is the reason or the main advantage you select the nitrile butadiene rubber waste?
I chose this waste nitrile gloves because considering the last 2 years, the usage of this nitrile gloves has increased remarkably due to the
increase here.
Yes, due to the corona pandemic and other our hospital systems in these nitrile gloves are used.
You are using the gloves, the corona, these blouses you are using that?
Yes, I considering the usage of that gloves.
Okay, since no more questions, we conclude this presentation. And it's the last presentation. I think, I hope that today is a very productive day of all of you, and today's IOURS platform provides an excellent opportunity to share your research finding with other researchers and academics, and opening an avenue to create a new ideas and innovative thinking for your future research, right? While thanking and appreciating all the participants and the researchers, we conclude this session. Thank you for joining, right?
Next session will be starting at 11:15. Please join with us by 11:15.
Good morning. I warmly welcome you to the International Open University Research Sessions IOURS 2022.
IOURS 2022 is an important annual event of the Open University of Sri Lanka. IOURS established itself as a high-caliber research forum that attracts not only researchers from the OUSL community but also other state universities and higher education institutes as well as overseas researchers, creating a forum for presenting and discussing valuable research findings leading to enriching experience to the researchers. IOURS significantly contributed to enhance the research culture among the OUSL staff members in ODL, open and distance learning, and disciplinary-based research areas, which directly inspired our staff members to participate at other international and national and international conferences by contributing holistic research findings. That IOURS 2022 will bring you renewed motivation and enthusiasm to engage in more productive research.
IOURS 2022 provides an opportunity for sharing knowledge created through research across various disciplines. I am particularly pleased with the choice of this year's theme, that is, Contemplations Towards Next Normal for a Smart Future, Directions and Dimensions. This is an approach emphasizes the requirement for educators and researchers to embark on creative thinking to formulate strategies to overcome unforeseen contingencies. Therefore, no doubt that this conference aims at breaking away from the traditional models of higher education and opening doors to new, innovative, creative and visionary conceptions. And this will also be a stepping stone for further development of Open University of Sri Lanka's national and international advocacy campaigns.
I'm delighted to introduce our chief guest, Professor Dr. Ebba Ossianelson. Professor Dr. Ebba Ossianelson from Sweden is an independent consultant, expert, influencer, and quality auditor in the field of open, flexible, online, and distance learning.
Thank you so much for the kind invitation to participate at your and contribute to your wonderful conference. It's a great pleasure and honor for me to be chief guest at your prominent conference with a timely theme on contemplation towards the next normal for a smart future, directions and dimensions.
The research sessions of the Open University of Sri Lanka is a very important annual event of the OUSL calendar that is indeed much looked forward by all tiers of the university. However, there is certainly a lot of groundwork that was involved in organizing the conference from inception to reality. Ladies and gentlemen, on behalf of the organizing committee, I'm honored to be here this morning to thank all those whose contributions have made today a reality.
The first keynote speech of IOURS 2022, which will be delivered by Professor Arjuna Parakram.
I see my role today as trying to do precisely that. I want to talk to you about the serious issues that we face. I want to encourage you to contradict me, to argue with me, to fight with me, so that we can produce a kind of engagement that goes beyond the platitudes of our times. So I hope, I'm very privileged to be here, and I hope that you will not decide that you made the wrong choice after you hear me talk. My title is Resisting the Aftershock Dogma, Rejecting Neoliberal Economic Policy as the Engine of Change in Educational Principles and Practice.
Welcome back to IOURS 2022. We will now commence the online session 5, parallel online session 3, under the theme Physical Sciences. Let me introduce our session chair. Our session chair will be Professor Susira Pereira. He is professor in physics and one of the head of Department of Physics, Faculty of Natural Sciences, Open University of Sri Lanka. I cordially invite Professor Susira Pereira to chair the session. Over to you, sir.
Thank you, Vasana. So, good morning and good morning, all of you, and welcome to the session 5 of IOURS 2022. So, in this session, there are about 5 presentations lined up. Before moving into the presentation, I would like to make a few announcements. The first one is the total allocated time for presentation and questions and answer is 15 minutes. So we are playing a pre-recorded video of the presentation. All the participants and the authors of the papers, please mute your microphone during the time we play the recording, and you can unmute them during the time of questions and answers. And definitely the presenter has to turn on his or her video and mic during the time of questions and answer. So we'll move to the first presentation for this session. The first presentation is 5-chloromethyl 8-hydroxyquinoline, a novel colorimetric sensor to detect ferrous 2 ions. The authors are K.A.P. Gaminda, D.T. Abesinghe, C.D. Jayasinghe, M.D.P.D. Costa, and R. Senthilnidhi. The paper will be presented by K.A.P. Gaminda.
I am Pasan Gavinda. Currently, I am following my PhD degree at the Open University of Sri Lanka. I graduated as a Bachelor of Science Biochemistry and Molecular Biology special degree holder from the University of Colombo, and I have recently completed my master's degree in Analytical Chemistry in the University of Colombo. So today I am going to present about the 5-chloromethyl 8-hydroxyquinoline, a novel colorimetric sensor to detect the Fe2. Let's see the significance of the Fe2. The ion is categorized as an essential metal ion due to its involvement in numerous biological processes. And one such process is the oxygen transportation and storage using the globin proteins. As we all know, The hemoglobin can bind to the 4 oxygen molecules simultaneously, and those will transport to the tissues via the blood circulation system. So the fusion of the Fe2 with the globin protein results the formation of the hemoglobin. Apart from that, Fe2 actively engaged in the DNA synthesis and repair process, also the electron transfer, enzymatic reactions, and energy productions. However, there are several disadvantages associated with the elevated Fe2 levels, such as increased rate in the aging process, neurological disorders such as Alzheimer's and Parkinson's, hepatitis, and it can also lead to the cancers. So therefore, efforts have been taken to develop a novel sensor capable of detecting Fe2 contaminations in the environment. So in this study, we used the 8-hydroxyquinoline to develop this sensor. So let's find out more about the 8-hydroxyquinoline. 8-hydroxyquinoline is a potent metal chelator that is utilized in various fields, such as the development of medicinal drugs, fluorescence markers, transition metal chelators, organic light emitting diodes, etc. So as you can see in the figure 1a, the 8-hydroxyquinoline is a bicyclic compound. It consists with the pyridine ring fused with the phenolic group. Depending on the position of the hydroxyl group, the compound name varies. When it comes to the 8-hydroxyquinoline, the hydroxyl group attach the 8th position of the compound. Therefore, it is known as the 8-hydroxyquinoline. And the figure 1b shows the possible reaction site of the 8-hydroxyquinoline. In this study, we synthesized the 5-chloromethyl 8-hydroxyquinoline and 8-hydroxyquinoline derivative, which exhibit remarkable colorimetric change in the presence of the Fe2. And it was utilized to develop our sensor to detect the Fe2. So let's move on to the material synthesis, the 5-chloromethyl 8-hydroxyquinoline. 0.05 mole of 8-hydroxyquinoline was mixed with 8 milliliters of conc hydrochloric acid and 8 milliliters of 37% formaldehyde. And the reaction mixture temperature was increased to 50 Celsius. And the hydrochloric acid gas was bubbled through the solution mixture for 1.5 hours. Then there's a sudden color change from brown color to bright yellow color. Then it was stirred for 6 hours. Afterward, it was allowed to settle down overnight. Then the solvent was stripped over using a filtration. Then the bright yellow solid was washed 3 times with acetone. Then it was vacuum dried using a vacuum oven at 25 Celsius. Afterward, the solid was characterized using the Fourier transform infrared spectroscopy. So, the results and discussion. The structural characterization based on the FTIR spectroscopy. The FTIR spectrum obtained for both 8-hydroxyquinoline and the 5-chloromethyl 8-hydroxyquinoline are shown in the graph. The blue color denotes the characteristic peaks for the 8-hydroxyquinoline, while the red color denotes the FTIR spectrum for the 5-chloromethyl 8-hydroxyquinoline. As we can see, both FTIR spectrums are approximately similar, and the new peaks obtained for the derivative indicate the formation of new bonds, proving that new substances have been formed. So, according to the FTIR spectrum, the vibrational peak at the 692 is characteristic for the carbon-chlorine stretching. This distinctive vibrational peak suggests the formation of the 5-chloromethyl 8-hydroxyquinoline, since all of the other chemical bonds are also available in the 8-hydroxyquinoline as well as the 5-chloromethyl 8-hydroxyquinoline. And the melting point of the 5-chloromethyl 8-hydroxyquinoline was estimated as 280 Celsius. Moving on, the results and discussion. The colorimetric detection of the Fe2 by the 5-chloromethyl 8-hydroxyquinoline. In the presence of the Fe2, the 5-chloromethyl 8-hydroxyquinoline solution shows a colorimetric change from yellow to green. The color intensity tends to increase with elevating metal concentration, and none of the metals such as aluminum, zinc, or lead were capable of changing the sensor's color from yellow to green. As you can see in the graph, there's a good linear correlation between the absorbance and the concentration of the Fe2. The conclusions and the recommendations. The 5-chloromethyl 8-hydroxyquinoline sensor exhibit an excellent linear relationship with a limit of detection of 0.04 plus or minus 0.1 parts per million. Compared to the other 8-hydroxyquinoline derivatives, the 5-chloromethyl 8-hydroxyquinoline is completely dissolved in water, and this facilitates the detection of the Fe2 in aqueous solutions without additional purification or concentration of the samples. However, further purification and the structural characterization are required to understand the mechanism involved in detecting the Fe2 by the 5-chloromethyl 8-hydroxyquinoline. So, this work was supported by the Accelerating Higher Education Expansion and Development Operations Sri Lanka, Development Oriented Research Grant number 28, the Open University of Sri Lanka. So, these are my references. Thank you.
Thank you very much, Gavinda, for your nice presentation. And now the presentation is open for questions and answers.
May I ask a question now? Am I audible?
Yes.
Yeah, I don't know why you are using 5-chloromethyl. What will happen if you use just 5-chloro only? Or is there any possibility you have checked whether having a substitution some other place rather than 5 position?
Sure, sir. These procedures are involved in the...
Gavinda, please unmute.
Sir, can you hear me now, sir?
Now, okay, yes.
Actually, sir, the procedures include, there are several procedures are used to attach this 5-chloromethyl compound to other positions. But the thing is, with the resources we have to go with this one, because those things were required highly sophisticated instruments such as higher temperatures, controllers, those kind of things, and other gases as well. So therefore, we thought of going with this method because it is easier to synthesize compared to the other methods.
Okay, right.
So I have one question. Is this chemical 5-chloromethyl 8-hydroxyquinoline, can't you buy it from the market from some chemical?
Actually, sir, there are, I think it's available in some, but there are not the 5-chloromethyl, some other places that, so we have to synthesize it manually. Most of the time we are using it because with the time it can degrade into some other compounds.
Okay. So when you dissolve this in water, it is you don't have any color, no? After when you
no,
attach,
when it dissolved in the distilled water, it turned into a yellow color, sir.
Then
With
it turned to red after absorption of ferrous too.
No, sir. With the addition of the ferrous, the color was changed into the green color.
Green color,
yes,
yellow
sir.
to green.
Yellow to green.
So what is the ratio between metal ion and your ligand ratio when you mix?
Actually, sir, it's 1:1.
1:1.
So are there any more questions from the audience? Since there are no any questions, so we thank the all the authors and the presenter for participating in IOURS. And we'll move to the next presentation.
Thank you, sir.
The title of the next presentation is Ferrous Chelation Activity of Annona muricata plant extract. The authors are NIS Dilshan, SK Rodrigo. The paper will be presented by NIS Dilshan. Over to you, Dilshan.
Welcome all of you for my presentation titled Ferrous Chelation Activity of Annona muricata plant extracts. I am Shanil Dilishan from the Department of Chemistry, the Open University of Sri Lanka. Let's see what are the natural products. Natural products are obtained from the different natural resources, plants, animals, and microbes. Natural products may be organisms, or the part of an organism, an extract, or pure compound. In our study, the plant extracts has been used as the natural product. Natural product can be defined as the secondary metabolites, and the active compounds isolated from natural sources play a major role in modern medicine. Annona muricata plant is an evergreen terrestrial tree. That plant has been selected for our study. Why we have selected it? Actually, it can be considered as a good candidate in traditional medications, and it is used for treating against different diseases such as diabetes, cancers, skin diseases, and the parasitic infections. As well as it can be considered as the best fruit that we are consuming in daily life. In this study, we are mainly focusing ferrous chelation activity. Ferrous is necessary for the continuation of the vital function of living organisms in different ways. But excess iron levels in body is quite toxic. In other way, formation of reactive oxygen species is catalyzed by ferrous ion. Reactive oxygen species formation leads to oxidative stress is the condition occurs in body as the result of imbalance between reactive oxygen species and antioxidants. So we need to get medications to control iron overload in human body. Metal chelation is the most important and primary clinical treatment which is used in case of heavy metal poisoning. But synthetic metal chelating agents cause some health problems, so the natural metal chelating agents are known to be safer than synthetic agents. So in our study, the major objectives are the extraction of plant materials using different extraction methods and the finding the best extraction method to investigation of ferrous chelation potential. An investigation of ferrous chelation potential of Annona muricata plant extracts. Let's see the experimental methodology we have followed in our research study. First, the plant materials, leaves, barks, and seeds were collected and dried well under ambient condition. Then they were ground to obtain the powder mixture. After that, the three materials were extracted using different three extraction methods: Soxhlet extraction method, shake extraction method, sonicate extraction method. Here the methanol was used as the solvent. The finally extracts were evaporated to remove excess solvent using the rotary evaporator and dried well in vacuum oven. Then we obtained crude extract samples. Then we have analyzed the ferrous chelation activity of obtained extracts. First, plant extracts, tris HCl, sodium chloride, and ferrous sulfate were mixed, and that mixture was incubated for 5 minutes. After that, 110-phenanthroline was added as the indicator. Finally, absorbance was measured at 510 nanometer using that equation. The ferrous chelation activity was calculated as an inhibition percentage. These are the results we have obtained in our research study. Here, each plant extract was subjected to ferrous chelation assay at the different concentration of extract with the positive control as EDTA. This table shows the ferrous chelating activity of Annona muricata plant extract prepared using oxalate extraction method. According to the results, bark has shown the promising activity higher than EDTA. Marginal activity can be observed with the leaf extract, while the seeds gave the weak activity. As same as this table shows the ferrous chelating activity of the extract prepared using the shake extraction method. According to the results, bark has shown the promising activity and others have shown weak activity. This table has shown the ferrous chelating activity of Annona muricata plant extract prepared using sonicate extraction method, as same as the bark has shown the promising activity. All results have been obtained in the study we have summarized in this graph. So according to the results, we can see the activity depends on the concentration and the plant material, and it is slightly changed accordingly with the extraction method. Every time the bark has shown the promising activity higher than EDTA, and the weak gave the weak activity, seeds gave the weak activity. 110-phenanthroline forms a complex with ferrous ions, while the presence of other chelating agents of plant extracts inhibit the formation of that complex. That is why we have observed the decreasement of the intensity of red color of that complex. Then we can calculate the inhibition percentage as the ferrous chelation activity using the absorbance value. According to the results, there are some conclusions we can mention. The extracts were observed to chelate the ferrous in a dose-dependent manner, and the plant material and the extraction method-dependent manner. Bark extracts have a significant ferrous chelation activity among the different extracts, and the activity decreases in this order. The bark has shown the promising activity, and the marginal activity can be observed with the leaf extract, as well as the seed gave weak activity. The shake and oxalate extraction methods are effective for bark extraction, whereas the tourniquet extraction method is effective for leaves, and oxalate method is suitable for the seed extraction. However, further studies, including the isolation of active compounds and their identification in vivo studies on the chelating agent, should be done in order to get further insight to this promising activity. These are the references I have used in my research study, and thank you very much for hearing my presentation. Thank you very much.
Thank you very much, Dilshan. So now the presentation is open for discussion, and if you have any questions, I think the presenter will be able to answer them.
Can I ask a question now? And you must have a look at the literature work. And what are the chemical constituents present in this bark of this extract?
Yes, sir. We are not going to check the constituents of the chemicals, but according to literature, the phenolic compound is available in high content in the bark extracts and colloids like that compounds.
Okay, but you must be seeing now bark contains something special rather than the seeds. So you must be have some guess. What are the guessing you have at the moment?
Phenolic compounds is available in high content because as the good antioxidant, that compound should have a ferrosylation ability, because in our body system, antioxidant power is increased by the ferrosylation. Ferrous is accelerated the antioxidant superoxide formations, reactive oxygen species formation.
Okay, thank you.
So I have a very simple question. What do you normally call this plant, Annona muricata?
Katu anodes.
Katu anode. Okay, thank you. So are there any more questions from the audience? Dilshana, why do you go for this particular plant in your research? Are there any special reason for selecting this particular plant?
Yes, according to literature, they have shown this plant has very promising antioxidant properties. That is why I have used this.
But that is not related to chelation of ferrous, no?
Normally, ferrous is chelate in our body. If the ferrous concentration is high in blood, so reactive oxygen formation is accelerated by the metals, heavy metals. That is why.
Right.
I think the way forward is to fractionate it and see which fraction is active and that what is the component present in that particular fraction.
Yes, sir. Isolation is still going on.
Thank you very much for your nice presentation, Dilshan. So that we can move to the next presentation online. The next presentation is IP separation axioms in ideal topological space, and the authors are S. Rakshana and P. Ilango. The paper will be presented by S. Rakshana. Over to you, Rakshana.
Hello everyone, I welcome you all to the International Open University Research Session 2022. It's a special for me to be here to present my presentation on IP separation axioms in ideal topological spaces. Before I start, let me introduce myself. My name is Sugunaraja Rakshana from Department of Mathematics, Faculty of Science, Eastern University, Sri Lanka. Now let's move on to the slides. This is the outline of my presentation. First of all, I'm going to talk about the introduction part. In topological spaces, there are many types of separation axioms. Here we discuss T0 space, T1 space, and T2 space. And also, we have many types of topology. Here we are working on ideal topological spaces. In 1990, Kratowski and Vaidyananda Swami introduced the notion of ideal in topological spaces. The separation axiom in ideal topological space was presented by Don Chew in 1995. After that, many researchers working in this area. In this study, IP open set are used to establish the new type of separation axiom is called IP separation axioms, which includes IP T0 space, IP T1 space and IP T2 space. And here also we compare our newly found IP separation axiom with the other already existing separation axioms in ideal topological spaces, as well as we consider some of their most important features. Next we consider the methodology part. Here I include some definition which are used to develop our newly found IP separation axiom. First, we consider the definition for ideal topological space. An ideal Iono topological space X is a non-empty collection of subset of X which satisfies the following properties. If I is an ideal on X, then X, tau, I is hold an ideal topological space. Next, give the definition for already existing separation axioms such as IG T0 space, IRG T0 space and alpha IG T0 space. Next, we consider the results part. Here I include the definition for IP T0 space, IP T1 space and IP T2 space and also consider some of their most important properties. So first definition for IP open set. A subset A of an ideal topological space X is said to be IP closed set if A star subset of U whenever A subset of U and U is pre-open. We define the complement of IP closed set is said to be an IP open set. This is the main definition for our IP separation axioms. Next definition for IP T0 space. An ideal topological space X is said to be IP T0 space if for each pair of distinct points x, y of X, there exists an IP open set containing one point but not the other. Next lemma says the comparison of our newly found IP T0 space with the other already existing T0 space, IRG T0 space, alpha IG T0 space and IG T0 space in ideal topological spaces. Theorem: every subspace of a IP T0 space is a IP T0 space. This is the proof for this theorem. Next theorem: if from X to Y be a IP absolute bijective map, if Y is IP T0 space, then X is IP T0 space. This is the proof for this theorem. Now we consider IP T1 space. Definition: an ideal topological space X is said to be IP T1 space if for each pair of distinct points x, y of X, there exists a pair of IP open sets, one containing X but not Y and other containing Y but not X. Next lemma says the comparison of our newly found IP T1 space with the other already existing IRG T1 space, alpha IG T1 space, IG T1 space, IP T0 space and T1 space. Next theorem: an ideal topological space X is said to be IP T1 space if and only if every singleton subset of X is IP closed set. So here we take X is IP T1 space and we need to prove that every singleton subset of X is IP closed set, and conversely we take that every singleton subset of X is IP closed, then we need to show that X is IP T1 space. So here is the proof. Next section: IP T2 space. Definition: an ideal topological space X is said to be IP T2 space if for each pair of distinct points x, y of X, there exists an IP open set U and V such that X belongs to U, Y belongs to V and U intersection V is equal to empty. Next lemma says the comparison of our newly found IPT2 space with the other already existing IRGT2 space, alpha IGT2 space and IGT2 space, and also we are comparing with the IPT1 space and T2 space. Proposition: if, G be a IP continuous map from X to Y and Y be an IPT2 space, then the set X belongs to X such that f of X is equal to g of X is a IP closed set. This is the proof for this proposition. Next theorem: the map f from X to Y be a one-to-one IP continuous map between ideal topological space X and Y being a T2 space, then X is a IPT2 space. This is the proof for this theorem. Finally, this brings me to the end of my presentation. Let me give you a summary of what I have talking about over the last few minutes. Here we introduce a new type of separation axioms in ideal topological space, namely IP separation axiom, by using IP open set, which includes IPT0 space, IPT1 space and IPT2 space. In addition, we look the certain important theorems and their interconnection with the other existing separation axioms in ideal topological spaces. These are some references I referred through my research work. Thank you for your attention.
Thank you, Rakshana, for your nice presentation. And now the forum is open for discussion and for any questions, and Rakshana will answer them. I think this presentation is related to pure mathematics. Maybe most of the audience will not be really understood what the aim of this particular presentation. Anyway, Rakshana, what do you mean by this T1, T2, T3? Is it related to time or?
No, sir. Sir, these are the separation axioms in topological spaces.
Space. Okay. Okay.
They are named as T1 space. In topological space, we have T1 space. That is a particular name for that one. T1 space, T2 space, T2, T3 space. Like that, we have more separation axioms in topological spaces. So here we are considering the ideal topological spaces. In ideal topological space, we are namely, that's a separate name for IPT1 space, because I found these IP by using these pre-open set, I use this IP separation axiom. So there's a new name for this one.
Thank you. So you have done this particular work for your undergraduate work or for your postgraduate research work?
It's an undergraduate work, sir.
Okay. Right. So are there any more questions from the audience? So if there are no more questions, so we'll thank the authors, all the authors and the presenter.
Thank you, sir.
So we'll move to the next presentation for this session. The title of the next presentation is PVA based B-honey and povidone iodine coaxial electrospun beads on string nanofibrous scaffold for controlled drug release. The authors are WACJ Venkapuliyarachchi, CA Totavathage, MAKI Dissanayaka, GKR Senadira. The paper will be presented by WACJ Venkapudi Arachi.
Good afternoon everyone. Today my presentation is woven around the research topic PVA to propanol-based B-honeycomb and pyridine sheet coaxial heterospun based on string nanofiber scaffold for controlled drug release. This is the outline of my presentation, which includes introduction with objectives, methodology, results and discussion, and finally the conclusion. In the introductory phase, I will be elaborating on the importance of wound healing dynamics. We consider wound normally as a damage to our skin. Roughly 5.7 million people in USA are affected by chronic wounds, and about $20 billion spent annually specifically on wound management. The stacked bar graph on the right shows the gradual increment of wound dressing market in accordance with the continents of the world. When we go parallel, focusing on the advancement of wound dressings and how the material is going to affect, on left, the figure shows the common types of wound dressings in use, such as bandages, films, and the talking point, nano or microfiber scaffolds. The classification of nanotype wound dressings are given below as passive, interactive, advanced, and smart dressing. We extend our research on the advanced type here. Choosing a polymeric material for wound dressing is a tough ask because it depends on the mechanical properties, antimicrobial properties, and biocompatibility. Based on previous literature, PVA has been the most effective synthetic polymer. So using this type of materials, nanofiber dressings can be made. In our project, we use beads on string nanofibers to fabricate the wound dressing for sustained drug release for wound healing. There is certain misconception that beaded fibers are something useless because of the lessened surface area, but it has shown promise and potential in drug loading and drug release. So pouncing on this fact and the hassle of normal nanofibers causing burst release, research studies done by Ki et al. And Somipat et al., we made the decision to prepare beaded nanofibers to understand its potential and possibility of incorporated drug releasing dynamics. So, the objectives in our project includes a methodical series approach to prepare beaded nanofibers by coaxial heterospinning the core solution PVA-based honey solution and sheet solution PVA-based pyridine, and also to adjust the drug release by controlling the size of particles for sustained drug release, avoiding burst release. For the preparation of solutions for coaxial heterospinning, we had to mix the solutions according to our unique design of weighted proportions. Weight over weight percentages of the two solutions could be seen in the left hand side table, where the weight percentages of core solution kept constant, while increasing the weight percentage of sheet solution, keeping the ratio PVA to pyridine as 4:1. These are the steps followed for the preparation of core and sheet solutions. Initially, we had to weigh the relevant amounts, and after mixing them, we had to manually stir. For the coaxial heterospinning process, we have certain parameters we had to adjust, namely spinning voltage, flow rates, separation, drum speed, sliding speed, and the needle size. For the fabrication of 3 samples, I changed only the flow rates and kept all other parameters fixed as given in the table. Initially, we had to feed the relevant core and shell solutions, and it reaches the coaxial spinneret after applying voltages and on. We can fabricate the beaded nanofibers on tea bag and the aluminum foil simultaneously. Under results and discussions, morphological characterization could be summarized in the following table, parallel to the scanning electron microscopic images, which depicts what has happened with the increase of sheet solution concentration from 7.5 to 12.5, while the core and sheet flow rates dropping from 0.5 to 0.1, resulting in the gradual change in morphology from more profound micro and nanoparticles to bead-joining nanofibers, which in turn proves the transition from coaxial electrospray to coaxial electrospin, The bar graph in general shows the ranges of particle sizes of the first two samples and then the fiber diameter and bead sizes of the third sample. FTIR characterization was used to identify the chemical structures and bond formation between povidone and bee honey when they are released to the wound. So in here, the stacked FTIR spectra and the peak shows that there is no new bond formations which will alter the original compounds, giving the hoped outcome. In vitro drug release profiles of bee honey and povidone was analyzed through UV spectroscopy separately for the three samples that we prepared, and the results showed that there is not much of burst release, while the release of profiles of bee honey in the three samples were similar. In povidone release profile, while increasing weight percentages, drug release rate has been decreased. Third sample having the best beaded nanofibers had the slower drug release, further backing the incorporated nature of povidone. ANOVA statistical analysis was done to data to understand the release behaviors of bee honey and povidone. So, the p-value of bee honey is greater than 0.05, while in povidone it is less than 0.05, portraying the significance of povidone on the release behavior. As our conclusions, beads on string nanofibers were successfully fabricated in sample 3 using a unique approach in the transition phase of coaxial electrode spraying to coaxial electrode spinning. Particle count and fiber diameters were controlled through sheet solution weight percentage and flow rates. This is the first time it has been tested to use the same base medium PVA as both core and sheet solutions to mix the relevant drug. Slow control sustained drug release of povidone and the natural antibiotic care of bee honey is an interesting combination for wound dressing applications. Further adjusting and improving this study could result in coaxial nanofibers, which will be studied in later experiments for drug release applications. I would like to thank everyone for listening to my presentation. Thank you very much.
Good afternoon, everyone. I am Podhanidhi Mageswaran, who did honours degree in chemistry at Southeastern University of Sri Lanka.
Thank you, Chaturanga, for your nice presentation. And now the forum is open for discussion and any questions. This povidone, Chaturanga, it's a solution, no? Solution in water.
So it's generally we call as betadine. So it's readily available in pharmaceutical industry.
Betadine, yes. So it is in solution form. So is it mixing with it is normally mixing with bee honey, no? Bee honey.
No, sir. It is generally a solution about 10% weight over volume solution. So it is mixed with certain medium so as to treat for the wounds. What I have done here is I have mixed this povidone with the polymer alcohol. So it is, and also I have used the medium as 2-propanol and water in order to change the electrohydrodynamics so as to electrospin.
Have you mixed bee honey also with?
Yes, separately I mixed polymer alcohol with bee honey as the core solution for the electrospinning. For the sheet solution, I have separately mixed polymer alcohol with betadine or the povidone. So in order to use the medium, I have used 2-propanol and as well as water, that is distilled water. In order to electrospin, you have to have certain balance between the electrohydrodynamics, that is the viscous force and the electric fields. So in order to balance it, that we have to use certain medium so as to electrospin. So in general, when it forms the in the coaxial spray technique, what happened is you get the beaded beads more of the beads. And when you increase the viscous force, by increasing the sheath weight percentage, what happens is it's going to transfer from coax electrospray to coax electrospin. So using that idea, our main target was to prepare a bead nanofiber, which is not much in use. So in order to fill that void, our research is more focused on that.
So the substrate that you have used is paper or something like that?
Generally, what we use in order for the testing, trial and testing, we used just the aluminum foil. But after further testing, what we did was we used a tea bag simultaneously with aluminum foil, which is attached to the particular collector drum, and so that we can do the electrospinning with much ease. So there won't be any issue if we use a thin tea bag. So actually, we can use this tea bag as a certain physical attachment to the wound instead of using gauze or anything else.
So if the audience have any more questions, so you can ask from the presenter. So if there are no more questions, so we'll thank the presenter and the author of this paper so that we can move to the next presentation in line. So this is the final presentation of this session today. So it is, the title is Evaluation of a Zinc 2 Phenolphthalein complex as a potential inorganic phosphate sensor. The authors are P. Maheshwaran and K. Ranasinghe. The paper will be presented by P. Maheshwaran. Over to you, Maheshwaran.
Good afternoon, everyone. I am Podhanidhi Mageswaran, who did honours degree in chemistry at Southeastern University of Sri Lanka. Today, I am here to discuss my research work on the topic of evaluation of zinc phenolphthalein as a potential inorganic phosphate sensor. These are my contents that I have planned to go throughout my presentation. Let me move on to the introduction part. Phosphorus is a limited nutrient needed for all life, most commonly in the form of phosphate ion. But here, I am specially focused on the inorganic phosphate in the environmental water bodies. The major sources of inorganic phosphate that enter into the water reservoirs are from the agricultural waste, industrial effluents, surface runoff, and from the domestic waste. These inorganic phosphates need to be detected in order to avoid the water pollution, to enhance the growth of crops and aqua plants, and also to perform the biological mechanisms. The appropriate quantity of the phosphate ions can be used by the vegetation and soil microbes for their normal growth. But higher concentration leads to the water quality problems, especially eutrophication, which causes turbidity, low oxygen, and bad odor. So, to avoid such extreme conditions, we set a goal to identify a potential sensor for monitoring inorganic phosphate in environmental water bodies. For this purpose, we designed EBT-based metal receptors to probe inorganic phosphate through indicator displacement assay. This is the general schematic representation of the indicator displacement assay, where the metal coordinated with the strong ligand L and the weak ligand EBT indicator. Initially, EBT forms reversible bond with the metal complex, and after the introduction of the phosphate ion, the metal complex displaces the EBT to give a calorimetric change. From this scheme, we can come to the point that the basic requirement for the indicator displacement assay is the affinity of metal complex for EBT must be lower than the affinity for the phosphate ion. Let me show you the structure of the selected metal complex, zinc phenolphthalein complex. It is in the octahedral geometry with two bidentate phenanthaline ligands. Now let me move on to the methodology part. The zinc phenanthaline complex was synthesized using a known procedure and the waste product was collected and dried over a vacuum. Then, to increase the purity, the complex was recrystallized through the slow evaporation method and stored for the further analysis. To confirm the purity and the complex formation, the sum of the characterization and stability analysis were carried out. In addition to that, zinc phenanthaline EBT complex formation and its sensing properties were analyzed. Let's turn to the research and discussion part. Here, in order to find out the stoichiometric ratio between the zinc phenanthaline complex and EBT, the Jobs plot of continuous variation method was used. Here, a series of solutions were prepared and the UV visible spectra were recorded and illustrated as shown in the graph. The absorbance data at 546 nanometer were extracted from this graph to draw the Jobs plot as shown here. From this plot, the obtained stoichiometric ratio between the zinc phenanthaline and EBT was 1:2. Along with the optimum pH of 10, this stoichiometric ratio was maintained throughout the whole experiment. Let me move on to the next slide to determine the suitability of zinc phenanthaline EBT complex as a calorimetric sensor. This is the graph showing the absorbance spectrum of EBT in black color line. The band maxima at 546 nanometer of EBT spectrum gradually redshifted to 565 nanometer upon the addition of the zinc phenanthaline complex. And simultaneously, a new band appeared at 600 nanometer. Those two new bands correlate the binding of the zinc phenanthaline to EBT. This spectral change shows its suitability as a calorimetric sensor. To confirm it further, Benesi-Hildebrand plot was drawn to determine the association constant of zinc phenanthaline towards the EBT complex. The obtained association constant was 2.73 into 10 to the power 3 per millimolarity and the dissociation constant was 3.66 into 10 to the power minus 4 millimolarity. In addition to that, association constant of zinc phenanthaline to phosphate ions was determined. For this purpose, the absorbance spectra for zinc phenanthaline EBT complex with varying concentration of phosphate ions were plotted as shown in the graph. And some of the data were extracted from this graph to draw the Benesi-Hildebrand plot as shown here. The obtained association constant was 1.6 into 10 to the power 4 per millimolarity and the dissociation constant was 6.08 into 10 to the power minus 5 millimolarity. Let's turn to the next slide to show the substitution reaction between zinc phenanthaline EBT complex and phosphate ions through the spectral changes. Here, the band maxima of EBT was redshifted to 565 nanometer and a new band appeared at 600 nanometer which correlate the binding of zinc phenanthaline to EBT. Those two new bands disappeared gradually upon the introduction of the phosphate ions into the zinc phenanthaline EBT sensor solution. It clearly shows that EBT displaced from the zinc phenanthaline complex by the phosphate ions. In addition to that, the obtained limit of detection from this absorbance plot was 0.087 millimolarity. It is the important performance in method validation. At last, interference study was carried out in order to make sure that none of the anions alter the assay result. Here, the change in color and spectra of zinc phenanthaline EBT complex in the basic medium was observed in the presence of different anions. An observable color change and expected spectral changes were observed only with the phosphate ions. So, we can confirm that phosphate ions are selective and sensitive towards the complex over other anions. Move on to the conclusion part. From my research work, I have concluded that the binding stoichiometry between zinc phenanthaline EBT complex is 1:2. The association constant of EBT to zinc phenanthaline complex was 1 order lower than the association constant of phosphate ions to zinc phenanthaline complex. That means zinc-phenolphthalein complex prefers phosphate ions over EBT. The dissociation constant of EBT from zinc-phenolphthalein complex was greater than that of the phosphate ion. That means EBT can easily be replaced by the phosphate ion. And also, limit of detection of the proposed phosphate sensor was found to be 0.087 millimolarity. I have planned to do my future study on the fluorometric analysis, isothermal calorimetric titration studies, and also to modify the metal complex to improve its sensitivity. These are my references that I have gone through to do my research work. Finally, I would like to thank my supervisor, Dr. Kohila Ranasinghe, for her constant and warm encouragement, thoughtful guidance, insightful discussion, critical comments, and patience. And I am very thankful to the head of the department, demonstrators, technical officers, and other staff of the chemistry and biology laboratories at Southeastern University of Sri Lanka. Finally, I would like to thank my parents, my family, and my friends for giving me the fullest support at every phase of my life. Thank you so much for this great opportunity.
Thank you. Thank you very much, Ms. Spontaneity, for your nice presentation. And now it is open for discussion. And if the audience have any questions for Ms. Spontaneity, you can ask from her.
Hello, I missed something. I think what is EBT stand for?
EBT is the area-chrome black tea indicator. Area-chrome black tea.
Oh.
That is one of the indicators.
All right, okay. And then what is the donor atom in this EBT?
Here, nitrogen. Nitrogen is the donor atom in the EBT. It donates lone pair of electrons to the zinc metal.
So only one donor atom present there.
No, actually two. There are two.
So why it doesn't chelate as a bidentate ligand?
Yeah, actually it chelate as the bidentate ligand. So
but you put EBT too. If it is bidentate ligand, you can have only one ligand.
Yeah, actually it binds in the two places like that. Actually,
do you know the structure of the EBT? I can't remember now.
Yeah, it has the nitrogen atoms, two nitrogen atoms. With the zinc-phenolphthalein complex, two EBT molecules are attached in different places. So one EBT joins with the two EBT molecules.
Okay. And have you done a test with, how it preferentially coordinate to phosphates? If you have a mixture of ions, do you know whether it's going to coordinate only to phosphorus, not to other ions? So if you are going to use a sensor, there may be other ions present in the solution. So can we use it for preferentially for phosphates?
Yeah, I separately check with the different anions. As in the interference study, I check with the different anions. It preferentially attached with the phosphate ions, inorganic phosphates.
So have you tried with a mixture of them and see what is the response?
No, actually I didn't check with the mixture, but I separately use those things.
Okay, right. Thank you.
Thank you, sir.
So will you be able to see a color change physically by this particular chelation with EBT, the phenolphthalein chelation with EBT?
Yeah, visually observe the color change.
What's the color change?
Initially, the EBT bind with the zinc-phenolphthalein complex to give the red color.
Uh-huh.
After the displacement of EBT, that means after the binding of the phosphate ions, it gives the blue color. So I observe the colorimetric change also.
Okay.
Excuse me, I want to make a small clarification there. Vadanidhi did a small mistake. I think she told that the donor atoms are nitrogen. Maybe she's excited and she got confused. Poda, do you want to try again? Try to remember the structure of EBT and can you recall what are the actual donor atoms are of EBT? You said 10 donors, right?
Yes, ma'am.
But there are two OH groups there. The oxygen is the bonding site.
Yeah, oxygen, OH groups in the.
Yeah.
Yeah.
Okay, it's clear from the replacement, they are not nitrogens. But I don't have the clue about the EBT at the moment. I don't know whether it's a bidentate ligand, might be oxygen and nitrogen. If you are going to have phosphates or the other simple ions, I don't think it's a bidentate EBT is going to be replaced easily.
Yeah.
So are there any more questions from the audience? Since we don't have any questions from the audience, we will thank the authors and the presenter of this particular presentation. And so with that, we are coming to the end of this session. So I would like to thank all the authors of the papers that we have presented in this session. And so I think the session would be, it was a very nice and fruitful one, so that some of this work can be carried out further for commercialization. So these kind of sensors maybe someday you can develop as commercially, you can develop for different practical purposes also. So thank you very much for that you have contributed for our IOURS 2022, and we hope to see you in the next year also with your work that you carried out in physical science field. Thank you all of you, and have a nice day.